Hey everyone, Siddhant here, and today we're going to talk about explicit two-sided unique neighbor expanders. And this is based on joint work with Tim Shea, Theo McKenzie, and Pedro Pardes. So let G be a bipartite graph, and let S be a subset of vertices on the left side of this graph. So here, you should think of S as being the bolded vertices on the left, and the neighbors of S are the bolded vertices on the right. We call a neighbor of S a unique neighbor of S if it has exactly one edge back to S. So in this particular case, the two vertices colored blue are the unique neighbors of S. And we call a graph a unique neighbor expander if every small set on the left has many unique neighbors on the right. So just to make this a little bit more quantitative, in a unique neighbor expander, for every subset of vertices which cover a small constant fraction of all the vertices, the number of unique neighbors of S must scale as d times the size of S times a small constant gamma, where d is the degree of all the vertices on the left. Okay, so this is a somewhat non-standard notion of expansion. So let's talk about how it compares to spectral expansion. So just to remind people of what spectral expansion is, um, given a graph G, it's going to have some adjacency matrix, which is an n by n matrix. And this n by n matrix is symmetric and is hence going to have n real eigenvalues. One of these eigenvalues is always going to be equal to d, uh, and it's going to correspond to the all once vector. And the second eigenvalue of G is a quantity that we call the spectral expansion. And a graph is a spectral expander if the second eigenvalue is bounded away from the first. Okay, so now why is spectral expansion an interesting notion? Uh, it's interesting and used a lot in TCS traditionally because it gives us a handle on many of the combinatorial properties in a graph. For example, if you know that the second eigenvalue is significantly smaller than d, then it implies that the graph has no sparse cuts. It implies that there's no dense small subgraphs. And also, you know that a random walk on this graph converges to the uniform distribution pretty rapidly. And since this has been an object of intense study due to its importance in coding theory and pseudorandomness, there's many known constructions based on algebraic methods, which are Cayley graphs, combinatorial methods like zigzag product, de-randomization, the method of interlacing polynomials, and so on. And just to give a benchmark of what one should be thinking of the second eigenvalue of the graph as, um, the second eigenvalue it is never going to be better than 2 times square root d minus 1. And graphs achieving this 2 root d minus 1 bound are known as Ramanujan graphs. Okay, so the first question one might have is, well, we have this like well-studied notion of spectral expansion, which gives us a handle on many combinatorial properties. Does it imply unique neighbor expansion? So concretely, let's say you have a Ramanujan graph, the best possible spectral expander. What can you say about the unique neighbor expansion in this graph? Okay, a problem of this flavor was first studied by Kahale in 1995, where he showed that the small set vertex expansion in a Ramanujan graph is at least d over 2, which is to say, for any subset of vertices S, the number of neighbors is going to be d over 2 times the size of that set. However, as you can see in this picture illustrated on the right, we have a subset S. It has d over 2 times as many neighbors, but every neighbor has two edges back to S. So in particular, having vertex expansion d over 2 alone is not enough to imply unique neighbor expansion. So Kahale's result falls short. But one might ask, uh, can Kahale's result be improved? And also, if it cannot be improved, is there some other way in which small spectral expansion implies small set unique neighbor expansion? And the answer to this is an emphatic no. In fact, we know that there exist Ramanujan graphs with where small sets have no unique neighbors at all. This was most recently proved in a work of Kamber and Kaufman. And there's also older results which establish a similar statement for near Ramanujan graphs. Okay, so now we've established that this notion of unique neighbor expansion is actually generally pretty different from the pre-existing notion of spectral expansion. And you might ask why one might care about unique neighbor expansion. To motivate this, let me present a simple application. So say you take a graph which is bipartite and is a unique neighbor expander with more vertices on the left than the right. And now define a code where the code word bits are assigned to the left vertices of this graph. And you consider an assignment of bits to be in the code if it satisfies all the parity checks, where a parity check entails choosing a right vertex, looking at all of its left neighbors, taking the XOR of the bits on its left neighbors, and checking if those are equal to 0. Okay, and it's a simple exercise to see that if this graph that you started with has unique neighbor expansion for sets of size delta times the total number of vertices on the left, then the distance of the resolving code is actually at least delta. Okay, so we showed some connections to coding theory. There's other applications that uh, we won't go over today. But this is a fairly well studied object, maybe not as well studied as spectral expansion, but still fair share of work on unique neighbor expanders. And in addition to the explicit constructions, there's a simple argument that shows that a random graph actually achieves the best possible unique neighbor expansion possible. Uh, okay, but there's one shortcoming of all the explicit constructions. They're all one-sided. That is, they only give expansion from the left to the right, but not necessarily vice versa. Okay, so now getting to the main subject of this talk, which is the notion of a two-sided unique neighbor expander. So a two-sided unique neighbor expander is a bipartite graph where every small set on the left has many unique neighbors on the right, many being the left degree times the size of the set times a small constant gamma. And similarly, every subset of the right also has many unique neighbors on the left. And in this work, we will see explicit constructions of two-sided bipartite unique neighbor expanders, where we can actually make the ratio of the number of vertices on the right to the number of vertices on the left any arbitrary constant. Okay, so why study this notion? It seemed like for the coding application that I showed earlier, one-sided unique neighbor expansion was sufficient. And a motivation for studying two-sided unique neighbor expansion comes from the study of quantum codes. So a work of Lin and Xie showed that if you have two-sided lossless expanders, lossless meaning the unique neighbor expansion is quantitatively as strong as possible. Um, and further, if you knew that these two-sided lossless expanders satisfied an additional algebraic property, then you could actually use these objects to construct very efficiently decodable quantum codes. And I guess another natural philosophical reason to study this problem is that random graphs have this property. Random graphs actually have very strong two-sided unique neighbor expansion. And the question is it possible to de-randomize this particular property via deterministic construction. And we make some progress towards this question. We show that for most choices of D1, D2, for example, you can think of D1 and D2 as being any pair of uh, large enough constant even numbers. You can construct an explicit family of graphs where all the left vertices have degree D1, all the right vertices have degree D2, and the graph is a two-sided unique neighbor expander. And actually, additionally, for sufficiently small sets, where sufficiently small is x of root log n, so something that grows faster than polylog, but maybe a little bit subpolynomial, we know that every set expands losslessly, in the sense they exhibit the strongest possible quantitative form of unique neighbor expansion. Okay, so now that I've mentioned the result, let me move on and describe the construction. So the construction is based on taking a product of two graphs. The first ingredient, uh, which we will call the base graph, you should think of as being a very large graph. So if your goal is to construct a two-sided unique neighbor expander on n vertices, then you should think of the base graph as having order n many vertices. And then the uh, second ingredient is a gadget graph, where you should think the gadget graph as being a constant size graph. And because it's constant size, you can make the gadget graph have as amazing properties as you'd like, but as long as graphs with those properties exist, because then because you get a brute force over the choice of gadget graph. Okay, and the particular properties that we will need in our base graph is that it's a tripartite graph comprising of three layers: the left, the middle, and the right. And the edges occur in two bipartite graphs, one bipartite graph between the left and middle, and another bipartite graph between the middle and right. And you should think of both these bipartite graphs as being spectral expanders. And you should think of the gadget graph as being a random graph. Okay, and I said we're going to take some sort of product of these two graphs, which we call the tripartite line product. So let me now describe what this product is. So what you do is, for each vertex in the middle, you look at the left neighbors of this vertex, which I'll call NL of V, and you look at the right neighbors of this vertex, which I'll call NR of V, and you place a copy of the gadget H, which is a bipartite random graph, between the left neighbors of V and the right neighbors of V. And you do this for every single vertex V. So just to illustrate, here the highlighted vertex in blue is V. V has four red edges going left, four red edges going right. I've highlighted the left neighbors of V and the right neighbors of V in purple. And then we put down a copy of H between the purple vertices, and I've denoted the copy of H in blue. Here's like a more clutter-free description of this individual copy of H. And then once you place down all the copies of H, you have a graph whose vertex set is the left and right side of the base graph, and the edges are between the left and right. So it's a bipartite graph on L and R, and the middle was basically used to decide how to place the gadgets. And actually, this graph is a unique neighbor expander where small sets expand losslessly. And with this, I shall conclude my talk. Thank you all for watching. And if you have any questions, you should feel free to email me and my co-authors. Any questions and feedback are appreciated. Thank you very much.